So let's look at an alternate one, which is from the 1980s. This is Draper and colleagues. Originally proposed to be used in cricket. It's the 505 agility, or the 505 change of directional test. Draper referred to it as the 505 agility test, but it is a change of directional test. And again, a change of directional speed. That's what we want. The player will sprint 15 metres. They then complete a complete 180-degree turn and then sprint back 5 metres. So I'll show you this in a schematic in a moment. So again, has a high degree of test-retest reliability, but fundamentally it doesn't take into account, because it's a test of change of direction, it doesn't take into account cognitive and reactive processing, which one would argue in cricket is quite important. So if, as a physiologist or a S&C coach in particular, you just want to know change of direction, I'm not worried about the decision the player makes, this may fit the bill in terms of cricket. So here's the plan. So what you have is a track which is 15 metres in length, and then at 10 metres, the 10 metre line, you put light gates. So the athlete will run 10 metres, they'll break the light gate. Now what you've got is you've got the turning line. Now of course what is happening is they've got a 5 metre area. Now think about this in terms of the schematic from Young again. Fundamentally what we understood was that key aspects in terms of change of direction were the reactive strength index, which is stretch shortening cycle. So now we've got this 5 metre block, we're trying to slow, we know that line's coming. So we know that the one thing that we've got in this test is we've got spatial certainty, we've got temporal uncertainty, because we don't know how quickly we're going to do this. So the net result is the athlete now starts to put the brakes on. They're applying eccentric force generation, deceleration. They turn, whether it be to the left or the right. So again, conforming to the definition, we get a difference between left and right. We can look at muscle imbalance. And then what they do is they now apply concentric force generation and accelerate out back through the timing gates. So in essence, what we're doing is we're measuring the time taken to decelerate and then re-accelerate. And in fact, you'll see it in this video here. So we've got this in slow motion, going through, back to hit through the gates. So there's the gates. Now watch. Notice now the brakes are coming on. Turns. And then re-accelerates. Okay, so let's watch that again. So running, so this is sprint speed up to 10 metres. So now he's got spatial certainty because they know what's coming. So now we've got eccentrics. So now we're putting the brakes on. You can hear it by the footsteps. He turns, and now we drive into concentric force generation, and we've now got concentric, we're using concentric strength and power to accelerate out of the movement. So you could see that quite nicely in that example. And we'll look at it again here. This is a head-on example. Same principle applies, but I just want you to watch. Remember that the gates are at 10 metres, and then the braking line is a further 5 metres on. Same thing applies. Running flat out. So watch, you'll see really neatly. Look at the brakes starting to come on. Starting to come on. Turns, now tries to accelerate, driving off and accelerating out. And of course we can then do that from the left side and the right side. So that's a really nice example in both of those of a change of direction, which is assessing potentially left and right imbalance, takes into account the eccentric and the concentric. Of course what it doesn't do is separate out the eccentric and the concentric. The way you could do that potentially is put a timing gate at the 15 metre line. How long does it take for them to go from the 10 metre line to the 15 metre line to turn and re-accelerate back through? But it certainly conforms to our definition of a test of change of direction. And it works in something like cricket because actually it works, it's fairly similar to the length of a track as a cricket wicket. Now, one of the things that authors have looked at is what happens at the start of the test, because this affects clearly the reliability of the test. So what they have looked at here is what happens if we go from a stationary start or we go from a flying start. And this is quite interesting. So if you look, just look first of all at the stationary mean. So the stationary mean is 2.84 plus or minus 0.22 seconds. That is the time taken to do the test. If you go with the flying, it's 2.52 plus or minus 0.17 seconds. They've also looked at this across different days. So is it repeatable across days? And actually what you can see, if you look at the stationary, it goes 288, 84, 84, 82. So very, very consistent across the test. The only one that is significantly different is stationary 1. If you look at the flyings, it goes 257, 255, 252. So they're getting more consistent, but only by the time they get to trials 3 and 4. Now this is really important because this tells us an awful lot. One, it tells us that our scores and our comparisons are going to be affected by whether we do a stationary start or do a flying start. That would also be the same, for example, if we were doing the zigzag test. Less so for the Illinois, because the Illinois really has got a lot of straight line sprint speed. But secondly, it's telling us about familiarization. Remember that it's not a case of just simply doing one trial and taking that score. It's going to be very much about accruing information so that you can get a reliable result. What this is actually saying is that theoretically, with a stationary start, you probably only need one practice trial, and then you could in essence take the next score if you really wanted to. What it's saying with flying is you need at least 2 practice trials before you get consistent results, because flying 3 and 4 are not significantly different, but trials 3 and 4 flying wise are both significantly different to trials 1 and 2. With the stationary, trials 2, 3 and 4 are not statistically different, but they are statistically different to what we have for trial 1. So the net result is it tells us both in terms of there are differences in the score. So if we're looking at repeatability, we've got to either always use a flying start or a stationary start, but it also tells us how many familiarization trials we need before we actually go into the test. Because if you just go in and say, well, I'll just go and we'll do a familiarization trial, then you go in, then it's going to affect your mean score in terms of taking an average across 3 trials, which is what you would be looking for. So really important kind of data set for us. And a fundamental question to ask is, which one is the most appropriate? Well, if you were doing something like cricket, you'd go from a stationary start, because a cricketer is not flying into the test. You want to make it as sport specific as well as being as valid and reliable as possible. So this certainly seems to be more valid than something like the Illinois and the zigzag tests, because we have only in essence got one change of direction, and it certainly seems to be quite reliable. And in fact, this is from a fairly recent paper from Barber and colleagues, and the results of this study, but in relation to what they're referring to, which is the 505, demonstrate a high within session and between sessions reliability for both versions of the 505 change of direction test. Both tests do, however, demonstrate learning effects between sessions. Performance in the 505 performed with a static start stabilises after 1 day of familiarisation, whereas the flying 505 appears to stabilise after 2 days of familiarisation. So in other words, although it's on days, you could argue actually within a day you need to do 2 familiarisations for the flying, and then you might do your 3 trials. So that's 5 goes at it. With the standing, you've got 1 familiarisation, then it seems to be consistent, then you do your 3 trials. So familiarisation is really important, because one of the fundamental things is, remember that in the zigzag test, Thomas and colleagues were saying that one of the things you don't want to have is a learning effect. You want to take learning out. And so we can basically account for that by having familiarisation trials. So this is from Shepherd and Young in 2006, and they wrote this. The research concluded the 505 test was the most valid test of agility examined, or change of direction, because it resulted in the highest correlation with acceleration in the turning phase. Okay, so it's got a correlation with another measure of change of direction. In turning phase, correlated strongly with top speed. The author's viewpoint was that the agility test should be independent of top speed, whereas acceleration was more related to the demands of a change of direction and reacceleration. So one of the issues that we referred to with the Illinois test was it was so fundamentally limited by its association with sprint speed. That top speed was driving so much of what was going on that it wasn't surprising that it was highly correlated, as was the same with that zigzag test. Whereas this test, because they're accelerating and they've only really got that 10-meter acceleration zone and then they're applying the brake, sprint speed is not a driving factor here. So although you've got an association, it's not a causal effect.